All right, everybody. Good morning. Thank you for coming in on this. I mean, it is going to be a bright, shiny day, a little on the chilly side, but we're almost in November now. And you know something, I'm looking out and we have a class of about almost 80. I think we have less than 20% showing up for class. I think there should be a slight reward for that. So I'm going to give you a pop quiz. Okay. All right. Don't worry. All you have to do is write your name on a piece of paper. All right. So I'll contemplate what I want to make that. I'm going to pass it around, sign it, pass it, so everybody has a chance to do it. That's your pop quiz. Okay. You can't fail. Yeah. All right. Okay. While that's happening, let's go ahead and start this. Remember, we started talking about the circulatory system last Thursday. I introduced you. I talked about the heart, how it works, what is the work of the heart, etc. Now we're talking about pathologies. This is where I left off. We were talking about thromboembolisms. All right. So basically, think of that as a blood clot or a piece of that atherosclerotic plaque that's broken off, and it then now is flowing down into the blood until it reaches a luminal space that won't allow it to pass. It's going to plug it. That means everything downstream of that is going to be deprived of blood, i.e. deprived of oxygen. So therefore, it will be those tissues will be subject to an ischemic reaction, right? If this happens in the corollary arteries of vasculature of the heart, that means we're depriving these working cardiomyocytes of oxygen, right? If it represents a substantial aspect of that circulatory part of it, let's go back one slide. So we're looking here. If it's maybe up here someplace, that means everything downstream is going to be ischemia. This can result in a non-functional set of ventricles. So what does that mean? That means the heart isn't functioning. It's not pumping blood. You're dead. That's immediate death. It can actually, let's say it's maybe down here someplace. It's enough to impair function, but you're still alive, but that has an extremely weakened heart. And sometime later, weeks, months, etc., you eventually succumb. All right. It may be such that you survive and with some impairment, or it could simply mean that you really aren't aware of there being an actual problem. All right, so it's not a clinical heart attack unless you go to the hospital. All right, so that's where I want to leave it. That's just kind of a summary what I ended up talking about last Thursday. What I also want to talk about is the cholesterol part, because I remember when I was talking about atherosclerosis, that begins as a cholesterol-like depositions underneath the endothelial cells of vasculature. All right. If we go back to the 1980s or something like that, cholesterol had a really bad name. Correspondingly, eggs had a really bad name because they have a certain degree of cholesterol. Everybody was told to hold back on your cholesterol consumptions. People were told to eat Cheerios because the oats in Cheerios would dilute out and remove the cholesterol. Don't think about what all the other shit that's in Cheerios. If you ever looked at the box, okay, never mind. So let's talk about what's called good and bad cholesterol. So this isn't only just referring to cholesterol, it's referring to lipids in general, because lipids are nonpolar, which means they're not soluble in plasma or blood. So in order to transport them, they have to be associated with transport proteins, just like steroid-based hormones, right? Now, so when you give blood, or when you go to a physician and you're asked to go to the lab and give blood, they're going to, generally speaking, they're going to do an analysis, and they're going to be looking at your HDL, LDL, and VLDL levels. All right. So what are they? This simply means there's a couple ways of thinking about it, but just think of it this way. Lipoproteins are designed to carry lipids in blood, right? That's what they're designed to do. Then we have three types that I want to mention. The HDL contain the most protein, so think about those as a squeezed out sponge. They have the capacity to bind any available cholesterol or other lipids, right? Now, the LDL are the low density. They have correspondingly less protein and are more saturated. And then we have the very low density, minimal amount of protein, primarily fat, and they can't carry anything else, right? What's also important here is basically one of the things is that the good cholesterol is responsible for transporting these fats to the liver for processing and removal. And otherwise, it's going to the tissues or potentially deposition underneath the endothelial cells. Now, that being said, I know I mentioned this prior, but cholesterol, most 80% of the cholesterol in your body right now, your body's making. You don't have to eat any cholesterol. Your body, it is a critical material and your body's going to make it. And what that means is, 80% of the cholesterol in your body is determined by that sperm and that egg. It's genetic, all right? Now, there's a huge range of the amount of cholesterol, depending, everyone here, your body's making different amounts, all right? Now, therefore, under most circumstances, you guys are all young. You're healthy, it doesn't matter, okay? It doesn't really matter whether you eat 5 eggs a day or what, and actually eggs don't matter, all right? It doesn't matter how fat you're stuffed, how much fat you're consuming. Now, as you get older, one of the things that happens, your body tends to make more cholesterol. I'm in that category. So, bless you. That means that and it doesn't matter how much I can watch my dietary intake of cholesterol, my body's making too much of it, which means they put me on a medicine called statins, which suppresses your body's production of cholesterol, and that keeps my levels down, all right? Now, what also happens is that if you have a genetic predisposition to have elevated cholesterol levels, then what happens is you have to be very careful of your dietary intake, okay? But if you don't really care about it, all right? In my younger decades, when I was your age, it didn't matter what I ate. It didn't impact my cholesterol levels. And I'm a Southerner, which means if it flies, swims, crawls, you eat it, okay? And cholesterol was a part of the diet. You didn't worry about it, all right? So basically, I have to watch. I don't eat most of that kind of material, those kinds of things anymore. But I still have to watch my body's overmaking it. All right. That may be you somewhere down the road. And it doesn't matter whether you're a vegetarian or not. Okay. Because your body's making it. All right. Now, let's change gears a moment. When we were talking about the pump, the heart is pumping blood. Let's talk about blood. What is blood? Other than talking about it as a transport medium for gases, for nutrients, for signaling molecules, for cells. All right? What is blood? Blood consists of, think about it as something as a cell-based colloidal suspension to a certain extent. All right? So what does it mean? It has a liquid and it has a cell component. Let's talk about that first. If you take a sample of blood from you, we take it in an anticoagulant-based tube so it doesn't clot, and then we spin that down at around 3,000 Gs for 10 minutes. What's going to happen? You're going to pull down all the cellular components. Not all the primary cell components. You're going to pull down 2 primary populations of cells. You're going to pull down red blood cells or erythrocytes. This represents approximately 50% of the volume in blood. These cells are responsible for transporting gases, oxygen and CO2. We'll get into more details about that when we get to the end of the semester talking about the respiratory system, but I'm introducing the cells here right now, all right? So their primary job is to carry oxygen to the tissues, all right? Now, aside from that, we have a much smaller population of immune cells referred to as white blood cells because they're white. They look white. If you spin it down and you have this yellowish straw-colored bottom, top, that is the plasma. That's the liquid portion. And it contains a whole bunch of solubilized stuff, which we'll get to. It also contains a cellular portion. That cell portion contains red blood cells and white blood cells. And the red blood cells contain hemoglobin, hence they're red, and the white blood cells do not, hence they're white. All right. So you remove that, so now we have about 50% of this is a cell component, both white as well as erythrocytes. You also contain something called platelets, if you spin it down enough. What are platelets? Platelets are the smallest cells in the body. The smallest cells in the body. We actually, when I'm studying where you were many decades ago, we didn't think of them as cells. We thought of them as cell fragments, right? Because they, all of the blood cells, whether they're red or white or platelets, everything is derived from bone marrow stromal stem cells, the hemopoietic stem cell population. In the case of platelets, they differentiate into megalokeratinocytes, which then they just bust up and release a whole bunch of platelets, these small materials. Obviously, they do not have nuclei. Similarly, I didn't mention this earlier, but your red blood cells also do not contain nuclei, right? Now, the plasma portion up here has dissolved stuff. It's got lots of proteins. It's got sugars and salts and sugar, et cetera, all right? But that's the acellular portion, right? Now, plasma represents, so if you take and keep this from coagulating and you spin it down, and you will separate your formed element, your formed portion, that's your cellular portion, from your non-cell portion. If, on the other hand, I take a sample of your blood and I let it clot before I spin it. Okay, so I let it clot. Now I spin it. I spin that down. I'm going to not only remove the cell part, I will remove the clot. Okay, the clot is a hydrogel formed from fibrinogen being cleaved to then form a hydrogel, and that gets pulled down. So what I'm left with, this part up here, that is, we think of as plasma with anticoagulants. If without anticoagulants, we call this serum. Serum and plasma. I want you to know the difference. Plasma is derived from blood that was not allowed to clot. Serum, you allow the blood to clot. Now, what is the difference between serum and plasma? There is some subtle differences because, again, in order to clot, we start with fibrinogen. It forms fibrin. This forms a hydrogel that gets pulled down. So anything that plus anything it binds to gets pulled down. So it's not going to be in serum. There are distinct differences of what are the dissolved elements in serum and plasma. Generally speaking, it all depends what you're looking for. If you're an endocrinologist and you're undergoing your various studies, evaluations, you want to look for a hormone X or something, it may or may not be in serum at the same concentration as in plasma. So that's why when you go to the blood lab and you're giving blood, usually they're going to want multiple tubes. One of those tubes will be for serum, one of those tubes will be for plasma. And that all depends on what the chemist is going to be evaluating, right? Right, so blood. What is it? This is what it is. So the next thing I want to touch base on is, let's talk about that hemostasis, all right? That hemostasis, that clot formation, right? So basically, what is it? So as blood is flowing through the various circuits, your two circuits, your pulmonary circuit and your systemic circuit, it's flowing through the vasculature, it's flowing through the chambers of the heart. All of anything that comes in contact with blood are endothelial cells. They line all the vasculature, they line all the chambers of the heart. So blood is flowing there. I want you to think about endothelial cells. First, I'll give you some additional information later, but think about endothelial cells as a Teflon coating. Everyone knows what Teflon is, right? Your Teflon coated fry pan makes it non-stick, right? So you can you can make your cheese sandwich or your egg, fry your egg or whatever, and it doesn't stick, right? Now, what happens if you got a roommate who, instead of using a silicone or a plastic spatula, uses a metal spatula? What do? It scratches off the coating, right? Now you have the exposed underneath metal, whether it's usually going to be aluminum, but whatever it is, it's sticky. So now you try to cook that egg and parts of it stick, or your cheese sandwich sticks because you no longer have a nice coating. Now let's translate that to vasculature. We have an injury to the vasculature. That means we have a disrupted endothelial cell population. All right. So some of those endothelial cells are removed. That means the underlying extracellular matrix is exposed. Now, let's now go back and return to those platelets. Those platelets are normally, under normal circumstances, when we have intact endothelial cells, they're just flowing through the system. But they're the ultimate stealth devices. What happens is, with this exposed extracellular matrix, the platelets have ECM, extracellular matrix binding proteins, receptors that bind to this matrix. When they bind to that matrix, they degranulate, which means they bust open and release their ingredients. They initiate a cascade of events that ultimately results in the formation of a blood clot. All right? So basically, what does that mean? I don't care so much about knowing everything here. What I'm interested in is that you realize the whole point of this is the job of those platelets are to be, they're just normally flowing in the blood. When, however, there's an injury, and let's say you're leaking, you've cut yourself and you've got a hole, blood is leaving your vasculature. Your body needs to plug it up. That's the role of the platelets. They are degranulated in these exposed ECMs with the injured vessel that then plugs the hole and you don't bleed to death, right? That's the whole concept of hemostasis. Now, what's important, and there's a whole string of cascade of events that ultimately lead to a clot formation. And a clot formation represents fibrinogen, which is a monomer, which is circulating in your blood right now in the plasma. But when platelets are activated, there's a whole realm of things which ultimately result in the activation of prothrombin to thrombin. Thrombin cleaves fibrinogen. The fibrinogen binds together as a polymer. It falls out of solution and it plugs the hole. All right? That's hemostasis. Now, there is a whole series and a multiple components that are involved in this clot formation. I'm not going to hold you responsible for knowing that in this class, but what I do want you to know, what initiates the cascade of events and what finalizes that cascade of events. Okay? Now, there's two things to initiate that cascade. The first one I've just talked about, and that's the activation of platelets and an injured vasculature. There is another component, which is basically your extrinsic pathway. The intrinsic pathway involves platelets. Now we also have the extrinsic pathway, which involves the release of something called tissue factor. These are injured tissues. They release this tissue factor, and that initiates the cascade. The ultimate effect is the same for both. Okay? We get a clot formation. All right? Now, We have a clot formation. We only need it there for so long, right? Now, remember when I was just talking about, I actually talked more about it, this thromboembolism. I touched base on it now, but I primarily touched base on it last Thursday. You have this clot that moves and clogs something. So you can have too much of a good thing. But let's say you plug the hole, eventually you want that fibrin to go away. So we can form a clot. We also need to get rid of a clot. And so the process of getting rid of a clot, the clot is basically fibrin, which is protein. So how do you get rid of protein in the body? You use an enzyme to destroy it. You use a protease to destroy that protein. All right? So basically, the protein that degrades is primarily responsible for degrading fibrin is plasmin. Now, one thing I mentioned that plasma contains a whole bunch of solubilized components. I have a colleague of mine who argues that the whole purpose of blood is not to carry oxygen. That is a function, but its primary function is to carry protease inhibitors to keep your body from digesting itself. That's how he argues it, because he's a biochemist, okay? But he's not wrong, all right? So if you actually look at the percentage of various proteins in the body, taking out albumin, which has a lot of things involving carrying lipid components as well as other things, a lot of the proteins are actually protease inhibitors. And their job is actually to keep your body from digesting itself, right? Now, that means that active proteases are rare. They're only activated when and where the body needs them, and they're rapidly deactivated under normal circumstances. So we have a fibrin clot. We need to get rid of that fibrin clot. Now, that's degraded. It is degraded by plasmin. Now, plasmin, as the active enzyme to degrade fibrinogen, has a half-life in blood of milliseconds. That's because of this huge concentration of various protease inhibitors. Okay? And that's because you don't want it to dissolve everything in your body. All right? So basically what happens is plasminogen binds to the fibrin. Here it's protected from the protease inhibitors. It has to be activated by another enzyme called plasminogen activators. And there's two types. There's tissue type plasminogen activator, and there's urokinase plasminogen activator. They convert plasminogen to plasmin. Plasmin is associated with the fibrin. It degrades the fibrin, and we get fibrin products. And we have degradation of the clot and removal of the clot. All right? That's fine. Now, let's put some clinical significance to this. Let's relate this to a thromboembolism. When I talked about a thromboembolism, I said that there can be, think about a fibrin clot, which is located in some sort of vascular area, and everything downstream is deprived of oxygen. In the case of the brain, we call that a stroke, right? Now, we can make use of these particular enzymes for therapeutic potential. One such is called tissue type plasminogen activator, or TPA. TPA, we've known about both of these plasminogen activators for many, many decades. However, tissue type plasminogen activator is a current standard treatment for stroke. Okay? So you have a patient with stroke comes in. There's some occlusion to the circulatory system to the brain. The person obviously is still alive, or they'll be going to the coroner or into the hospital. But basically, that means that there is some disruption of blood supply. Now, there is a very narrow window. There's about a 2-hour window. The person's still alive. You want to recover as much functionality as possible. So what you want to do is reestablish the circulation in the brain. You want to remove the clot. Okay? How do you remove the clot? It's basically fibrin. So if I give, say, TPA, it will destroy the clot, reestablish the circulation. If I do that early enough, I can minimize the damage. Okay? So I can reduce the ischemic effect downstream. I have a short window, about 2 hours, to accomplish this. After that, the ischemic damage is done. All right. Or I have more damage than without it. Now, so the way this works is that you would give a stroke patient, you want to start them on TPA. The TPA is, your body makes TPA, but you're not giving a big dose of it. It's going to go to on that fibrin clot that's clogging the vessels. It's basically fibrin. There's plasminogen bound to it. It's just not getting activated as well as it should be. By putting this huge bolus of TPA, you really activate it. It degrades the clot. You reestablish circulation. Okay, you remove the ischemic effect. Now, I give you an example. My dad, a few decades ago, he lived on our farm in Kentucky. This is in the middle of nowhere. The closest town, small town, is about 6 miles away. It's a small town. The hospitals are basically, and that, as with most things in rural U.S. today, most of them are just stops to get to a different place. The closest major hospital was about an hour and a half away. All right. Very standard these days. However, that being said, this little hospital is very well equipped. I actually know the physician. He's old as the hills. He's older than I am, but he knows everything and keeps up on everything. So what happened is my father had a stroke. All right. My brother happened to be there, called the hospital. They said, get him here. On the way there, they were prepping to give him TPA. The moment he got to the hospital, in about 15 minutes, they put him on a TPA drip. He still had an hour and a half to go, but he was getting treated on the way to the actual health facility. And he got out of it with minimal down effects. And it was all because of timing. You would be hard pressed here to get that timing treatment. Even if I had a stroke here, going over there, I would be stuck in the emergency room getting processed before they would even start anything. All right. The advantage there is like, yeah, Dr. Flowers knew my dad. He knew his history, said, get him over here. We'll have everything ready to go. All right. So that is that golden window, right? Okay. We've talked about the pump. We've talked about the blood. Let's talk about all those blood vessels now, because the circuits, I've mentioned the circuits as the pulmonary circuit and the systemic circuit. Let's now talk about what is that. So let's focus, to keep this discussion simple. I want to focus on the systemic circuit. Remember, that's delivering to blood everywhere but the lungs. All right. It begins with the aorta, which is exiting the left ventricle. It then ends with the blood being dumped into the right atrium from the superior vena cava. Okay? We're with me now. So let's talk about what is that vasculature. So as I mentioned, it begins with the aorta. That's a single blood vessel. It is also the largest blood vessel in the body because this is feeding the largest circulatory aspect. Okay? That blood vessel is getting the most pressure because the pressure is coming from the source, the left ventricle. So you have one, and so basically it has to be a thick wall in order to resist the pressure of the blood exiting the left ventricle. It also has a cross-sectional area of 4.5 centimeters squared. Okay. Now, that means that, so the blood leaves that, it enters the aorta. The aorta starts to branch into the large arteries. They're getting smaller, right? Because we're dispersing the blood from one vessel to many vessels. All right, so we get to our large arteries. There can be several hundred of these. They would then be, obviously, we're further away, so the thickness of the wall is less because you have distribution of blood across a larger surface area. The surface area for these individual, the internal radius, let's go with that, is 0.2 centimeters, considerably less than the aorta, but you have you have a lot of them. You have several hundred of them. So we multiply the surface area for one times all the numbers, and that goes up to 20 centimeters squared. All right. So that's a much larger total surface area for that blood to be dispersed through. Even though they're smaller vessels, and we'll get into what that means for terms of flow, there's just more overall greater surface area for the blood to pass through. All right. We now then get to the arterioles. These are the end of the arteries. Remember, what's an artery? That are the vessel where the blood is flowing away from the heart. So now we get to the arteries. All right. These are much, much, much smaller. We have basically 500,000 of them. Wall thickness is much less. We have, even though their internal radius is 30 microns, if we count the greater number of them, their total cross-sectional area is 400 centimeters squared. All right. Now we reach the transition point. That's what the capillaries are. They are the transition between the artery and the vein. Right. This is where the purpose of arteries is for gas distribution, for nutrient exchange at the tissue level. That means they are the thinnest and they are the smallest of the vessels. You also have the most of them. You got 10 billion of the little suckers. All right. And they're approximately 1 micron thick. This is to facilitate exchange. Remember your Fick's law. And we drop on down. And they're only 3.5 microns. They cannot be any smaller than 3.5 microns. Why? Because the diameter of a red blood cell is 7 microns. And red blood cells got to squeeze through. Yeah, sure, it doesn't have a nucleus. It can deform to a certain extent, but it's got to pass through that tube unhindered. All right, so there is a lower limit to the size of a capillary. The capillary is the point of gas exchange, nutrient exchange, waste exchange, etc. And now at this point, it's transitioning from an artery to a vein, and we're flowing back to the heart, back to that right atrium. All right. So now we're talking about veins. So we have our large veins, which are the equivalent of our large arteries, several hundred of them. They don't have to be thick because this far away from the heart, the pressure is less, and we'll get to that in a moment. But they get bigger. Their internal radius is 0.5 microns, and they represent a total cross-sectional area of 40 centimeters squared. Finally, the return to the right atrium and the last of that systemic circuit. These are the vena cava. You got 2 of them, and they're 1.5 millimeters thick. They're 3 centimeters in radius, a total of 18 centimeters squared in cross-sectional area. All right. So we start with one big tube, a hell of a lot of little tubes in the middle, and then basically 2 tubes equivalent at the end of things. All right. So this is the anatomy of the systemic circuit. Again, we have our arteries, we have our veins, the capillaries, the transition point. Let me ask you a question, because I didn't ask this earlier on last Thursday. How many of you had in high school, you had an anatomy lab where you maybe got a fetal pig or a rat or something like that? Nobody. Okay. So usually what happens when you get these, they'll put latex dot, they'll inject latex to replace the blood. So it makes it easier to find the blood vessels and dissect them. And a lot of times it'll not just be red, it'll be red and blue. Red is to denote arteries and blue is to denote veins. Let me ask you a question. Is this always correct?
No, it would be, so since pulmonary artery is oxygen rich, it would.
Pulmonary artery is oxygen rich.
Oxygen poor.
Good. Okay, you got it. Okay. So it all depends on which circuit we're talking about. So if we're talking about the pulmonary circuit, the blood that enters the pulmonary circuit, that is the pulmonary artery, is furthest away from the lungs. So it's the least oxygenated of the blood, right? when it's being returned via the pulmonary vein, is the most oxygen rich because it's closest to the lungs. When we then go to the pulmonary, enter the systemic circuit, the aorta, the beginning of the artery, is still closest, so it's oxygen rich. And by the time it gets returned to the vena cava, is oxygen poor. So always remember that the definition of an artery is just where blood is moving away from the heart, and a vein is blood moving back to the heart. The capillary represents the transition point. It has nothing to do with oxygenation. Okay. Okay, now we've talked about the pump, we've talked about the blood, we've talked about the vessels. Let's start getting into how the blood is moving through the system. But before I get there, I want to just throw this here. These are endothelial cells. Remember, I already told you that they line all the chambers and vessels. They play a lot of roles. They're not just a Teflon coating. They also play critical roles in that they are also endocrine cells. They will secrete vasoactive substances which can influence blood flow. And we'll get into that later. They can also, if you have an injured, the endothelial cells can express hormones which can facilitate healing. They also, their removal is where we get platelets formed and all of that. So they play a variety of things, okay? But now let's talk about blood flow. I want to talk about blood flow because this is important. All right, so before I talk about blood flow, let's get some laws in place. You may have be familiar with some of this, maybe some of you in chemical engineering, but let's talk about, I was a pipeline testing engineer many decades ago, which basically meant that I was in the oil fields and I tested either gas or oil lines, all right? And it's no different from that versus your blood vessels. They're tubes with fluid flowing through them. Doesn't matter. The laws are all the same. So the first law I want to talk about is Laplace's law, okay? And Laplace's law, what it says is a cylindrical vessel, the wall tension is proportional to the internal pressure times the radius, all right? So that means that tension is equal to pressure times the radius of that cylinder, right? That's the first law, Laplace's law. The second one is Pascal's law. In Pascal's law, the fluid flowing through a vessel encounters resistance associated with the walls of that vessel, right? So that means that there is frictional forces that are on the outer walls which will impair the fluid flow. So if you're in the center of that lumen, there is less frictional resistance. As you move to the outside, you get more frictional resistance, okay? Now, what does this mean? Let me give you some examples. I don't think I can control shades. Let's see if I can control the shades from here. Good. Okay. All right. So let's deal with two vessels. All right. One is twice the diameter of the other. All right. So we have vessel 1 at 10 mils, and we have, and notice how here's vessel 1, vessel 2. Okay, vessel 2 is 2 times the radius of vessel 1, right? The resistance to vessel 2 represents the resistance is 1/16 of vessel 1. How does that work? All right. So what this means is even though I've only doubled the radius, or i.e. the diameter, what that's going to do is means that it's 16 times that of vessel 1 because it's 1 over the radius to the 4th power. All right. So there's a disproportionate rapid increase in resistance as I decrease or as I increase that. All right. I'm going to reduce the pressure. All right. Now we can also go over here, and that we can also state that blood flow through a tube is dependent upon pressure difference. All right. So pressure difference, what does that mean? That means that as I have a greater pressure difference, that's one end versus the other, I'm going to have greater flow. All right. So that means if we get up here, we have 50 millimeters of mercury on the left side, we have 10 millimeters on the right, we have a delta P of 40 millimeters of mercury, right? If we drop down here, we have 90 millimeters of mercury on the left, 10 millimeters, we have 80. So they're going to have flow rate. It's going to be twice, the pressure is twice, so the flow rate is going to be greater. Because the pressure difference is greater. Okay? Now, let me emphasize, we're talking about pressure differences, delta P. If we talk about here, we have 90 and 10, and we have 180 and 100, the delta P is the same, which means the overall the pressure difference is 0, right? So it's pressure difference. So the rate of flow is the same. It's just that this one is overall greater pressure. The downside is it's over greater pressure. So there is a greater possibility at this greater pressure for it to rupture the vessel versus up here. That's one of the reasons we're concerned with high blood pressure, because high blood pressure means your heart has to work because we have greater resistance to blood entering the circuits, but it also is putting additional pressure on those vessels and they're subject to rupture. Okay? Okay. All right. Let's move on down. Whoops. There we go. Now, so I hope you appreciate if I decrease the radius or the diameter of the vessel, that's going to increase the resistance to flow. Okay, that's going to increase pressure. If I increase, that's going to have the opposite effect because of the laws we just talked about. All right. Now, the next thing to remember, I went over the anatomy of the blood vessels, right? Now, what I want you to remember is that that is not static. That can change. Your vasculature, a blood vessel does not only consist of a tube structure lined with endothelial cells. There's also, as I talked about last Thursday, there can be smooth muscle cells. That's what these cells are here in this scanning electron micrograph. Now, these are muscle cells. What happens when they contract? They're wrapped around this vessel. If they contract, they get shorter, which means that they're going to reduce the diameter of this tube. All right. Now, what I want you to appreciate is this, is that this vascular, especially the small vasculature within, say, the systemic circuit, is under something called tone. All right. That means it's not that those smooth muscle cells are not maximally relaxed or maximally contracted. They're somewhere in between. What does that mean? That means that your blood vessel radius can either increase or decreasing depending on what you want to do. All right. So we call it vasoconstriction if it's getting smaller, vasodilation if it's getting bigger. Right. So basically, your blood vessels are under tone. They're partially contracted or partially relaxed, however we should use it. And what happens under vasoconstriction, what they're going to do is those muscle cells are going to contract. They're going to make the luminal space, that cross-sectional space, smaller. This increases the frictional forces. This is going to reduce flow. This increases pressure, right? On the other hand, vasodilation is going to have the opposite effect. It's going to increase the luminal cross-sectional area, reduce pressure, increase flow, right? So what you're seeing here is your blood vessels can change from moment to moment, depending on whether you want to have vasoconstriction or vasodilation. So what's going to influence vasoconstriction? So in vasoconstriction, what happens is, and what we can, it all depends. We can either increase or decrease flow depending on where it is in that system. So let's say that if under vasoconstriction, that's going to create overall greater pressure. So for over the whole system, that means I'm going to be moving blood more efficiently. All right. So if I have a system where I ask you guys to stand up and run in place for 5 minutes, that's means your skeletal cells need more oxygen to stay above their anaerobic threshold, right? So I need to deliver more blood. All right. That means I need to change the distribution of blood through that systemic circuit. So I need to shift more blood to those exercising muscle cells. And it's a closed loop. So if I'm going to direct more to that, I've got to deprive something somewhere else. All right. So how do I do that? By differentially vasoconstricting various vessels, I can, number one, I can result in an overall increase in total blood pressure, but I can also begin to divert that to various areas of need. All right. So that's why your blood vessels have the ability to change in size. Right. So under issues of where, for instance, I have a greater requirement for oxygen, I'm exercising, I need to remove the CO2 that I'm generating from these exercising muscles. And then of course, I'm being stimulated by sympathetic nervous system. All of this is going to result in vasoconstriction, right? The opposite effect, as I reduce O2 and so forth, maybe I want to, it's not that big a deal. I've reduced myogenic activity. I can then have the opposite effect. All right. Also, for instance, again, this is the wrong time of year to think about this, but let's say you go outside and you start to get hot, or you're inside and you're getting hot. Your body is, you are a homeotherm, so now you need to get rid of all that extra heat. How are you going to do that? What's going to happen is you're going to get vasodilation of the vessels underneath your skin. This facilitates the delivery of blood to the surface, and that facilitates the loss of exchange between here and the outside. All right. Okay. We don't want to get into sweating and all that. All right. Now, so your vessels are not fixed in size. They change depending on the situation. All right. Now, let's go back. Having said all of that, let's go and talked about the anatomy. Let's talk about pressure through this systemic circuit. So that means the blood is entering the aorta, it's returning via the vena cava. All right. Now, remember that the heart, how does it work? It contracts and relaxes. It contracts and relaxes. So therefore, what's happening is that as the ventricles contract, all we care about is the left ventricle here. It's going to force blood into the systemic circuit. When it relaxes, there will be no pressure, right? There's only pressure during contraction. It's reloading from its respective left atrium during relaxation. What we call this is, therefore, blood flowing through the systemic circuit is under what we refer to as pulsatile flow. It's not continuous. There isn't a pump that's going continuously rotating like a centrifugal pump. It is a pulsatile pump. The heart is a pulsatile pump. There's periodic. There's pressure, no pressure, pressure, no pressure. So every time that left ventricle contracts, it's going to generate 120 millimeters of mercury of pressure. Right? This is enough to enter the systemic circuit because it overrides the pressure existing in the systemic circuit. Now, we mentioned systolic and diastolic pressure. Let me reemphasize that systolic pressure, bless you, is the pressure during ventricular contraction. Diastolic pressure is the pressure under relaxation. Okay? Now, the pressure within the left ventricle during contraction or under systole reaches 120 millimeters of mercury. During diastole, when it's relaxing, the pressure is 0. So it goes from 0 to 120, 0 to 120, 0 to 120, or 0 to 120, 0, etc. Okay? That's pulsatile flow. And there's only flow out of the ventricle during systole. All right? Now, the blood, so that is the pressure within the ventricle. However, remember, there is blood within the systemic circuit. So there is pressure within the systemic circuit. So the pressure in the systemic circuit can never be 0 or you're dead. All right? So there is a pre-existing pressure. Let's say the mean pressure is around 90 millimeters of mercury, 95 millimeters of mercury. The mean being the mean between systolic and diastolic. So at the aorta, what you're going to see is you're going to see the maximal change during pulsatile flow. So during systole, and since it's that close to the heart, it's going to be 120. It's going to go up to 120 to reflect the same as the left ventricle. However, it will never go to 0 during diastole. It will only go down to around 85. Okay? Because that's filled with blood. It's under pressure. Right? Now, what that means is, so every time you have a heartbeat, you have up and down, up and down, up and down, 120, 0, 120, 0. We drop over here. We have 120, 85, 120, 85, 120, 85. But we're getting further away from the heart source, that left ventricle. And that aorta is branching. We get all of this the smaller yet large arteries involved. They're getting further away. And we find that as we get further away, there is less of a difference between systole and diastole. They're both decreasing, as we see here. Right? And especially we see this in the arterioles just before we enter the capillaries. We start to see big differences. Now, overall, the mean pressure is going down throughout because we're getting further and further away from the left ventricle. Now, note here that we're going to cross the capillaries. This is the transition point. There's still a pressure difference on one end of the arteries or not, because otherwise we wouldn't have flow. But note that we no longer see periodicity. Okay? We don't see a systole-diastole difference in pressure anymore. They're converged to a mean pressure. And this will continue not only passing through the capillaries, but in the whole vein aspect in its return. Note also that there is a continual loss of pressure through the system. So by the time blood is returned to the right atrium, the pressure is basically 0. So you can ask yourself, well, wait a minute, how can I have flow? Where's it going? What's happening? And this is just pressure difference. These are just pressure differences. Note that there's a continual loss in pressure throughout the circuit. How do we maintain flow? Right? Through that circuit. So that gets us to the next thing I want to talk about. So if we talk about blood flow, despite this change in vessels size, blood flow is constant. Blood flow through the entire systemic circuit is constant. Notice it does not change. Right? Notice that, but wait a minute, okay, but there's a huge, so what I want to talk about is, let's drop down here. Here's the anatomy that I talked about. I'm showing it visually. So here's the aorta, here's the vena cava. We start out with a big one. It gets to be a lot of little small ones. Remember, there's 10 billion of these capillaries. Then it goes in the opposite direction, right? Now, if we look at the total cross-sectional area, remember, that's the vessel's cross-sectional area times the number of vessels. So remember, you have 6,000 centimeters squared for the capillaries versus around 4.5 for the aorta. So you have significantly larger cross-sectional area, all right? That's key. It's the total cross-sectional area, all right? And that's associated here. What's the flow rate? I didn't say overall blood flow. I'm talking about the velocity of flow. What is the velocity of flow? The velocity of flow is, by definition, remember our Laplace's law and so forth, is going to be slowest because we have the most resistance at the capillaries, because this is where we want to have exchange. So we need to have not impaired, but we want to have the slowest flow so we can facilitate exchange. Remember, Fick's. All right? So this is your velocity of flow. All right? So the point is this. I asked you the question. So despite these anatomical changes, we maintain an overall constant flow through the system. Now, remember that the purpose of the capillaries is to have exchange between the blood and the tissue. So we want to have the lowest velocity of flow to facilitate this process. In order to achieve this, we have to have the smallest diameter of tubes to give us the most resistance to create that effect. To overcome and maintain a constant flow rate, we have to compensate by having a hell of a lot of them, 10 billion of those capillaries. So despite they're only big enough to allow a red blood cell to pass, this results in tremendous resistance to flow velocity. Overall, we have maintained flow rate. All right. Another way of thinking about this is we call this the lake effect. All right. So let me tell you an analogy. All right. It's still not too cold. So you want to go out for one last canoe trip and the upper reaches of Michigan or Wisconsin, wherever. Okay. Let's just say Minnesota or Canada, whatever, doesn't matter. Okay. So you're on a little river. And it's got a current, which means that you only have to use your paddles to steer, right? Because the current is taking you along. Now, this particular river dumps into a natural lake, okay? So as you're approaching this lake, you're only using the paddle to steer. You're not using it for propulsion purposes. As you enter the lake and get further away from where you entered the lake, you find out that in order to maintain the same rate of motion, you have to start using your paddle. You have to dip it in more frequently in order to maintain your same speed, okay? When you get in the middle of the lake, you have to use maximal paddling effort in order to maintain speed, okay? Now, what you see when you get to the middle of the lake, you look across the lake and you see the exiting river from that lake. So you're paddling for that because you want to continue your trip. As you get toward where the lake is dumping into that river, you find out, contraire, you don't have to paddle as much because you're speeding up, all right? Now, what that means is the fluid within that lake is not static, it's under flow conditions. It's just that the flow seems to be very, very low because it's spread out across a larger area versus being compressed in the river that's entering the lake or the river that's leaving the lake. All right. So we call this the lake effect. It's the same rate of flow overall. It's just distributed over a larger area. So you don't see it. Okay. So please be aware of this. This is a critical aspect in terms of how the circulatory system works. Okay. Now, I already alluded to this in that you can change this I can alter this by, well, let's say this. Let's say that I'm doing exercise, right? And I want to shift more blood to those exercising muscles. Okay? The only way I can do that is depriving some other tissues of their blood supply, right? So during exercise, what do I need to think about? I need to maximize the delivery of blood to those exercising muscles. What do I not need to worry about? I don't need to worry about my kidneys working. They can be on hold for a little bit. I don't have to worry about digestion of breakfast that I just ate. That can wait for a little bit. So I minimize blood flow to those just enough to keep those tissues alive and functional, but they don't need to do all the stuff they normally need to do. Okay? So I have to deliver excess blood to those skeletal muscles. What do I also need to do? Number one, I do not want to impact the blood going to the brain. I need to maintain that at a constant rate. Now, what else do I need to do? If you remember when I talked about skeletal muscles, I said they were responsible for you maintaining your core body temperature because What is the product of muscle contraction relaxation? Heat. Okay. So during exercise, what are you doing? You're exercising. You're generating heat. The more you exercise, the more heat you're generating. You need to get rid of it. You need to disperse it. So what you will also do is you will also direct more blood vessels to the surface of your skin so that you can facilitate heat loss. Okay. So all of that means that, for instance, let's go back here. Let's say that this is your digestion and your urinary system. These are your skeletal system here. Let's just keep it simple. So under exercise, you want to divert more to this set of pathways. So you're going to start to plug these up, reduce it, create greater resistance so that you will divert more blood flowing through here and here. All right. That's just the way you want to think about it. How does that work? That works with vasoconstriction, specialized vasoconstriction, vasodilation within those vessels, depending on where they're at. Okay. And so this is basically what you can see here. I mean, we can't change we cannot. Now, one of the things that happens is this. What happens if I have a great increase in vasodilation? What am I going to do to the volume within that circuit? I'm going to increase it. If I increase the volume, what am I going to do to pressure? Reduce it. Okay. If I do the opposite effect, if I do vasoconstriction, I'm going to increase pressure, right? Because I've decreased volume. Right. So remember that, and we'll come back and visit that. All right. This is basically things that you can change, things you can't change, and so forth. You can look at this on your own. I'm not going to go over that. All right. Now, we've talked about overall blood flow through the system. Let's focus on the capillaries. Why? Because the capillaries are where things happen. This is where exchange between the blood and the tissues occurs. Another way of thinking about arteries, their purpose is just to deliver blood to the capillaries. The purpose of the veins is to return blood from the capillaries to the heart. That's it. It's just transport. It's just transport. All critical exchange between the tissues, the non-vascularized tissues in the body, and blood occurs at the capillary. So the capillary is where everything happens. The veins and arteries are just transporting to and from the capillaries. Right? So what that means, think Fick's law again. So let's get to a capillary. Here are examples of capillary structure. Let's start up here. Capillaries have just enough luminal area to allow a red blood cell to pass through. It can't be any smaller because it'd be occluded and you would have ischemia, right? Now, so it needs, thinking Fick's law, it needs to be the thinnest. That's why the vessels are the thinnest in order, because the thinner the membrane, the easier it is to have transport, all right? Now, in addition, you will have your endothelial cells. You have this matrix which holds everything together. You may have some pericytes. Don't worry about what they do. We won't talk about it in this class. But basically, there can also be pores. That means where two endothelial cells don't actually meet. So you can have not only, we'll talk about transport. Transport has to go across this vessel wall. The vessel wall consists of endothelial cells. The endothelial cells can have gaps or holes between cells, and this means that things they can bypass the endothelial cell. They either go through the endothelial cell or bypass the endothelial cell, all right? So you can have tissues which typically have that have fenestrations or holes that allow for enhanced movement of materials. Or if we go to the nervous system, remember we talked about the blood-brain barrier, you don't have those fenestrations or holes, and you have additional astrocytes which create additional barriers to transport from the blood into the brain tissue, all right? So it depends on where these capillaries are. Now, so you can, depending on what tissues those capillaries are, the capillaries have either enhanced or a lesser degree of fenestrations or holes to facilitate transport. Now, aside from bypassing, everything has to, so either things go through the holes or the pores, or things have to go through the cell. If things are going through the endothelial cell, go back to your introductory lectures when we talked about transport across plasma membrane. If the material is soluble across that plasma membrane, it just diffuses down its concentration gradient, right? So if you're in the tissues, that means you're furthest away from the lungs. So that means the tissues are utilizing oxygen. So they're pulling oxygen out. So that means there's more oxygen in the blood than out. So oxygen will leave the blood going to the tissues. Those metabolizing cells are regenerating CO2. CO2 is a greater concentration in the tissues versus the blood. So CO2 is going to flow into the blood from the tissues. The tissues are using sugars and glucose, so glucose is going to flow out, all right? However, glucose is not permeable across the plasma membrane, so it has to be transported across, as is amino acids and proteins, etc. So exactly what we covered in the introductory will determine how, so things have either go through the plasma membrane of the endothelial cell or they have to go through a hole, okay? And if they go through the hole, they have to be small enough to fit through the hole. All right. Now, so basically, this is general. So your non-polar materials just go down their concentration gradient, either in or out. Your plasma proteins, they tend to be stuck because they're too large. They can't fit through the holes. They're not a transport mechanism. They stay in the blood. All right. Some amino acids and so forth will have to get transported. All right. So again, what I want to reemphasize and come back and revisit this. So here is your systemic circuit. We have a heart, your blood, your arteries are bringing blood to the tissues. Here is where we have the exchange between plasma and the interstitial compartment of the tissues. All right. So what is important is the relative concentration difference between the plasma component and the interstitial component, especially for gases and things like that can freely diffuse. Right? And then, of course, the artery is to get blood to the capillaries. The vein is to get blood back to the heart. All right. And everything goes down its concentration gradient, tends to. However, certain things are not capable of transport. They stay in the blood. Certain things have to have some form of facilitated diffusion or facilitated transport across the membrane. Either way. All right. Okay. You know something? I am going to stop here because I see I have 10 minutes left in class. I need at least 15 minutes to talk about these next couple of slides. So this is a good place for me to stop. Okay. So I'm going to stop here and we will finish up the circulatory system day after tomorrow on Thursday. Right.